We are Antonio, Garrett, and George, and our final project is playing shuffleboard through frictional contact with hybrid force position controller. A shuffleboard is a game played on a very long table, as you can see in the video. The game is played in rounds, one-on-one. Each round, players take turns shoving 8 pucks each down the table to scoring zones, with players being able to knock each other's pucks out of the scoring zones. The person who reaches 21 points first wins the game. With that said, essential skills in the game are puck placement and strategy. We focus on the former, as this game offers a convenient way to study how we can enable robots to accurately slide objects.
We explore the use of hybrid force position control for precision sliding. Sliding is a hard manipulation task that requires a robot to simultaneously control the position of an object while maintaining contact with it and exerting enough force to control it, but not so much as to break it. Sliding and launching things inherently extends the robot's reach. This can prove beneficial in settings where a robot needs to move a fragile object or when it needs to move a heavy object that cannot be thrown outside of its normal operating range.
Our goal was to slide the puck to a goal location on the other half of the table to within 10 centimeters. Our sliding controller has 2 main parts, the most fundamental of which is a custom operational space controller. It controls the position of the end effector in the XY plane of the world frame and applies a specified force along the Z direction of the world frame. The customization comes in the form of a feed-forward force in the XY plane that counteracts the friction between the puck and the table. With this controller, we are able to press down on the puck and slide it around on the table like you would slide cards on a table. The second part is a trajectory generator. It takes the desired final resting position of the puck as well as its starting location. It uses basic kinematic equations as well as an estimate of the friction between the puck and the table to calculate both a Z force trajectory and an XY position trajectory for the end effector. The XY trajectory satisfies that the end effector starts where the puck is, only presses down for 1 second, then moves to satisfy a final position and velocity. The position is determined by our cutoff of 1 meter from the table, and the velocity is solved for by the simple kinematic equation that v final squared equals v initial squared minus 2 mu gd, where d is displacement and mu g is the deceleration due to friction.
These first few graphs show the absolute distance from the target location as well as a spray chart of where pucks ended up relative to the target locations when we gave the pucks a thrown trajectory. This serves as a baseline for industry research throwing actions as a way to extend beyond basic pick-and-place manipulation. As you can see, many issues arise when throwing objects, including dynamics in the air and on the ground once the object falls. This can greatly affect the imposition of the object as seen with these charts. These next graphs show the same distance from target location and spray chart, only we are using our controller to push pucks using our hydroelastic contact. As you can see, the distance from the relative point on average is less as well as the spray chart. We tested this over 100 trials along with randomly generated points across the board. The data we collected shows an 80% increase in accuracy for a set target point and 63% increase in accuracy for randomly selected points.
When we ran the controller, one of the first things we learned was just how sensitive the system was to gain tuning. If the gains were too aggressive, the end effector slipped off the puck. On the other hand, if they were too soft, the puck wouldn't launch consistently. Maintaining contact became absolutely critical, as even tiny separations led to large errors several meters down the table. We also saw how small modeling errors, especially those in friction and the predicted release velocity, amplified noticeably with distance. Our friction feed-forward term helped, but long-range shots still revealed undershoot. Finally, some limitations came from the hardware itself, like the EWA's 1 meter reach, and our simplified friction model, which couldn't capture small variations across the table surface. Overall, we showed that a hybrid force position controller combined with a simple physics-based trajectory model can reliably slide a puck to targets outside the robot's reach. Across both fixed and random targets, the controller produced far more accurate and consistent launches than throwing. The results also revealed the limits of analytic sliding control, as it performs very well at short and medium distances, but long-range shots magnify small errors in friction or release velocity. These insights point toward clear next steps, such as online friction estimation and better release geometry. Beyond the shuffleboard, the same framework could generalize to warehouse robots, service robots, or even strategic non-prehensile manipulation where controlled collisions matter.